Hey, good morning. Good morning. Hey, Omar, welcome back. Welcome back. Hey, you're good now. You're much better. Yeah, awesome, awesome. Okay, all right. Um, well, you know what? As not only in 2A, I think in 2B, maybe 2C. I don't know. Some people got sick, and it's worse in 2B and 2C because every day counts in 2B and 2C, and I think what would be good is if these the people who got sick and missed a bunch of days for whatever reason, they can continue to attend class and so on, and they can just re-enroll next quarter or whenever it's offered again, and you would have completed all the quests anyway, unofficially before. So you could basically just swim through the official quarter, helping other people and having a great time, essentially. Right, that's actually happening in CS2C right now. There's a bunch of students who've actually finished all the red quests before the quarter even started, and they're just hanging around, having a great time, making interesting posts and so on. I think it's a great deal of fun. And you'll find out that essentially any job, really, not just computer science, but I think I know because I've been in computer science. 90% of the fun of being in any job, right? Any job is not getting stuff done. Well, it's getting stuff done is also cool, but a great deal of fun is just interacting with your colleagues, because they're also doing cool stuff, and then they'll look at what you're doing and, hey, that's really cool, I'm going to take that idea and try it in what I'm doing. All of that is really, really great, and I think it's fantastic to experience that. So if you're sick at all, the thing you can consider, the only thing I so Foothill has this I don't know, maybe it's government. Okay, maybe it's a government regulation that if someone who has done a class and passed it with a low grade, like C or something, cannot re-enroll in that class, because it's like the government paying. Really, if you think about it, these classes that you're getting in, at Foothill College and so on, they don't cost, like, you're only paying $150 or $200 per class. Yes. But think about it. If you go to Stanford or some of these other colleges, you pay a lot more money for the same kind of classes, and but they're private, and it is so that should essentially present to the students the real picture, saying, hey, that's really what it actually costs most of the time. But the government, the taxpayers, will subsidize your experience by paying a lot of the money that it's going to cost you directly to the teachers and the college. Right, so these institutions that are not private get a lot of money from the government that make up for the fees that ordinary people pay for the elite colleges. So therefore, I think the government has this rule saying you can't do this course more than once, especially not so much here in computer science, maybe, but I think in art. Okay, in art, we had some students, ceramics, okay, ceramics. We had some students who were really, they were good and they did everything, but they found out at the end of the last quarter of their art classes that they were really good, and people liked to buy what they were making, right? And setting up your own kiln and having these incredible facilities, like thousands and thousands of glazes and chemicals, get anything you want. That's not easy to get get out there. You have to pay a lot of money to go to some professional kilns to get that effect. So a lot of students basically just said, I just pay $150 to Foothill and redo these courses because I can do all my art pieces right there in our ceramics lab. So I think that was part of the reason. We're not like super duper strict on these things, but sometimes the Foothill may come clamping down. So if that is the case, and somehow you missed a lot of classes, but you caught up and you feel that you're at risk of passing the class, right, with a C or something, right, you can let me know, and we can come, I can give you some advice as to what you can do to make sure that you're still eligible to do this class next quarter. Okay, so yeah. All right. Anyway, it's great progress. If you look at the recorded lectures, if you look at the Reddit, I think I'm looking at great progress. Lots of people are engaged in class. Week 6, having engaged students in week six, I think is great. You have to be really, really lucky as a professor to get a bunch of students who are continuing to be, continue to be engaged all the way through. And so I'm very pleased and happy and thankful to you guys for doing that. What you can do is today, like I promised last class, no new material. Okay, like no new tasks, right? No new material. Although some new material may sneak in, but it's not like midterm, right? So you don't have to worry about material. So you can. What we can do today is we can just talk about any concept in any of the things that we've talked about so far. Just bring it up and we can talk about that. We can work through examples, we can code together, we can code a lot of this. Well, let's say, right, because we're going to be doing lots, potentially, I don't know, right? Potentially we're going to be covering lots and lots of different concepts. We won't take one big project, right? And say, oh, we're going to work through it from beginning to end. What we can do is, when someone says, this particular thing is confusing to me, we just do a little snippet, okay? Like one like 10 line fragment of code that exposes the nitty-gritty details of the thing that is confusing to that student, and then hopefully that'll be useful to everybody. And then we can do lots and lots of those things. Okay, so or if nobody has any ideas, we just pick up that game that who coded last class? Was it Sabrina? So it was, no, Sabrina. Sabrina coded last class. Yeah, great. Okay, we can pick up the code that Sabrina coded, and then we can play. Right? It was actually a pretty cool game. I was trying to win against myself. But it's actually pretty cool with the penalties that we've instituted and all for incorrect bam bam bam. So we can play that game a few times, and maybe in the course of playing the game you get more ideas, or things that, oh, I don't know how that works. Let's go over that in more detail. All of that is open, open territory today. Okay, so absolutely feel absolutely free to ask any doubt, any question that you may have regarding any topic we've covered, okay, starting all the way from data representation, although data representation is not going to be the focus of the midterm, okay, because you already had a quiz on data representation, right? So it won't be the focus. However, you'll need to know about data representation, right, for the midterm, because in the midterm, I think there are some questions. Actually, you know what? I saw on the Reddit, someone posted a question saying, hey, there was a question in the practice midterm with bits, 1024 bits or something, right? And what is the most significant bit and listing, right? And why is that question in the midterm practice? Because that really is a data representation thing. Well, however, unlike style questions, for which I'm willing to happy to reinstate points. If you get a style question, it doesn't matter if you get it wrong, you'll get the point back. Okay, so that's a freebie point for you. I can't do the same thing for data representation, although I can tell you that there shouldn't be a great deal of data representation questions in the midterm. But if there are, you still have to get them right. And more of the data representation knowledge as you progress through 2A, 2B, and 2C will not be directly data representation, like what is the, bits and so on, but it'll be more like, if this is that kind of data type, will it work in this program, right? Or should you change the data type to something else? And you'd only know that by knowing data representation, right? Because you need to know whether it's a signed quantity or an unsigned quantity, or whether it needs to be 4 bytes long or 2 bytes long or 1 byte long. Yeah. Sometimes in question number 3 of 2B, right? In 2B, you're going to be dealing with data that is on 1 bit. Right, 1 bit, not even 1 byte, 1 bit data, right? So you got to be fiddling with byte and changing individual bits in there, because that bit is my data. I'm going to change that. And so you'll be fiddling with that. So that's why getting a really solid handle on data representation before you get into 2B and 2C will really help. So don't underestimate that just because it's the first week and it's gone. Also because I think other sections, I'm pretty sure at Foothill, nobody else teaches data representation in a 1A or 2A or 3A course in the first week. And I'm pretty sure that they don't do it in other colleges either. I look at some of these other colleges. In fact, what is it? When I get time, I just, sometimes I browse what are the other colleges offering for the entry-level computer science courses, and I see a few, and they're all teaching stuff that is in the syllabus, but not spending the first week or first few days talking about data representation, unfortunately. Well, actually, there is one exception. Well, maybe there, I don't know. All right. So this course, Harvard has a CS50 course, which is also online, which is free and online. Anybody can enroll in it. And and then there's a lecturer there. I think his name is David Mallon, right? And he teaches that. And his lectures are also video, YouTube. It's on YouTube. You can see his videos. I think maybe he talks about data representation during the very first class, or first or two classes. First two classes, he talks about data representation, bits and bytes, and so on. I haven't seen other professors do that. And why is that? Because they're just, if a professor doesn't teach data representation, they're making their own job hard. Okay, I can tell you that, because comparing my own experience from the days before, when I didn't used to do that, my own job later on was hard because students didn't know sometimes the program misbehaves, and then the professor has to go and say, well, that's why it's working and not working, right? And whereas if the student knew data representation, they would have figured it out themselves. And so they're having to do a lot of these things. So I think it'll greatly help. So to bedtime reading. After you've done all the questions, you can do bedtime reading if you're still unsure about some of these concepts. Okay. So other than that, I don't have anything particular to say today, because it's it's also a midterm day. You don't have to take the midterm in a hurry right now. Okay, unless you're pressed for time and all. Take it easy and take your test later in the evening, right after your this is a tip. I don't know, maybe it's just for me, right? Here's a tip I found that worked for me during my student days, right? During my student days, and coincidentally, I discovered it. And I don't know if I did have enough samples, at least 5 or 6 samples, I think 5 or 6 data points. But I think if I did more experiments, I would have probably confirmed it, right? Not proved it wrong. I think that taking an exam on an empty stomach gives you like 2 or 3% more points, right? I don't know, right? For me, okay? Because I think that if I take an exam on a full stomach and I'm completely happy, I don't tend to do such a good job on the exam. Partly because I think some part of my brain wants to sleep, or say, I'm good and happy. I just want to relax now. However, if I'm hungry, and I'm saying, well, I got to do this before I can get a bite to eat, I'm just focused more, and I can get through. I think it's just for me, right? So you can try that. In the safe confines of a college course, you can actually try that and see if it works for you. But still, so you can take the test before your dinner, maybe, just before your dinner, and it's one hour. Once you start it, the clock will start ticking. And then you have 1 hour, but you can take it whenever you want. So it's kind of cool that way. All right. So I don't have anything particular to say today. Okay. I'm just here because I'm so happy to see you all. Because you're all doing some cool stuff, right? You're all doing great stuff. And I see your posts, you're making interesting observations. So, and plus we have these games that we've developed. I think we've created like 4 or 5 different games now in class, right? This is week 6, 4 or 5, and some of these are actually pretty cool. And people like Erica, Hannah, Namrata, all of you guys, right? So they've taken the game and take injected their own flavor to it, right? Flavor, variations. Those are the interesting parts. Once you get past the first thing, okay, that's how it is. It's cool. Then people start looking for variations of that. And saying, hey, you know what? It's the same thing, but it's got this interesting variation. So try this. So those are all really cool. And so we can do that. Okay. If you want to just warm up, we can just play Sabrina's game. Okay. It's on Reddit. Someone posted it on Reddit. We can absolutely start off by playing the game. It doesn't have to be that particular game. You can pick any of the games that we've developed so far in class. What is it? What was the first one we did was changing your name. I remember vowels. Yeah, vowels get changed. And I think it was Namrata created a version of that and posted it on Reddit. And so that one, what else? So I don't know. I forget. I don't want to waste time thinking about, which ones we did. But you can pick any of those games, okay? And say, let's play a couple of rounds. And in the process of playing this game, you can work in your mind, work it out in your mind and say, hey, that's why it's doing this, okay? It's got that loop. And as the things are happening on screen, you can say, that part is being handled by that if statement. This part is being handled by the for loop and so on. And that will basically seal this, knowledge in your mind more firmly. And so we can try that if you want, unless you already have questions, right? If you already have questions about any of these concepts that we've talked about before, yeah, bring them up. We can talk. We can also code. We can code. We can say, hey, I'm looking at the screen today, and every one of you has had a chance. Yang, you haven't had a chance. You said you'll code today, right? Yeah. If we code, you can code. And Ryan is here today. Ryan, I haven't seen you in class before. Do you have a conflict at 8 a.m. or something?
Yeah, I have work, my job, but I tried to after the first couple of weeks. It just got really hectic. Sorry about that.
I see. All right. Okay. No worries. Good to see you. Good to see you here. If you don't like your colleagues, you can always inflict this entire lecture on them and say, hey, come to the conference room. We'll put it up on the big screen. We'll all watch the video and code something together. Okay. And so. Yeah. Okay. So Ryan can also code, and then Hannah is there. You can code. Next week we'll have some stuff to do with objects and pointers, and I think because you're already familiar with objects and all, so you'll have a much better experience coding some of the stuff that we'll do from next week onwards. So after we talk about objects, okay. So we have 3 people in class today that haven't coded so far. Hey, Antonio, you did code, right? You did code. Can hear you. Can hear you. I think he coded.
Can you hear me now?
Yeah, I can hear you.
I have not coded so far.
Oh, you haven't? Oh, for
No.
some reason. Yeah. Okay. So we actually have 4 people who haven't coded. We have a number of chances coming up, so everybody will get a chance to code, and that's great. And you can also talk to all these other people who have coded, and it's actually a fun experience, right? Sabrina was the most recent one. Sabrina, well, it was fun last class, wasn't it, to code?
Yeah, it was actually kind of stressful.
I was hoping you wouldn't say that, but that's okay. That's okay. Why is it stressful? It's yeah, okay. Maybe it's stressful for students because it's the first time on screen coding in front of people. It is a bit stressful, but the way to get over it, I think, is just to do it, right? And like Nike says, no?
I think it's just having everybody watch me.
Yeah, that's I know, right? Yeah, that is stressful. Absolutely. It's like public speaking, isn't it? Like public speaking.
Yeah, pretty much. Yeah. And then trying to figure out what you said and then processing it fast. Yeah.
And public speaking is always, first time. I remember, when I was in school, my first public speaking thing was I used some poem, right? I had to remember this poem and recite it on stage. And the guy before me picked up some long poem, and he did a perfect job. Okay, and so I thought, well, anyway, there's no way I'm going to do better than that. And I was there. I could literally feel all the butterflies in my stomach. Okay, this is fluttering around, and people watching me. So and then I spoke to my teacher and say, I can't do this, please don't do this. And then she said, you know what, I think you did a reasonable job out there, but the antidote to, stage fright is just being on stage many times. And so, and then the following weeks, she just pulled me up every time after that. And then, miraculously it disappeared, right? After about 4 or 5 times, it disappeared. And I went and thanked her afterwards, saying, well, I don't know how you knew this, but it actually did work for me. Because after a while, I think we figure out, being in the public eye, all of the discomfort it raises is actually illusory, because it's all what we think other people are thinking. Most of the time we don't even know what we are thinking ourselves. Actually, that's not true, but most of the time, most people, I think, build up their internal universes with their own mental pictures of what other people are thinking of, what other people's worldviews are. But think about how many places that could go wrong, right? With even just one person, there's a scope for a million mismatches there, right? You could be thinking one thing and that person could be, but the behavior could fit, right? The intersection of the behavior could fit both pictures, but the pictures could be completely different. And so there's so many different people and interacting with so many people, and in a stage with so many people in front, we were all thinking, oh, that person is probably thinking I'm doing a bad job. I actually remember one time I did karaoke in a bar, right? So, and all my friends said, don't go, you're a bad singer. Okay. I said, no, I'm going to go and sing. And then my co-singer, she was, what was the song? It was, oh my gosh, it was a UB40 song. Red Wine or something like that. Yeah, it was a UB40 Red Wine. And then it was, and she did a great job. But later on I remembered, I was thinking about it, and I said, I made a total fool of myself because I couldn't hold a tune at all, and I was there singing with someone who could sing really well. And then that kept me up at, saying, wow, what a nasty job. I made a fool of myself. But then after that, I realized, I had a great time, actually. Despite making a fool of myself, I had a great time. And that really was what mattered, because all those other people who maybe thought I was not doing a good job, they would have forgotten. They're not, they think about it, right? Everybody has a life. Everybody has great things to go and achieve and do. They're not going to be latching on to something that happened out there that it's not important. Okay, so these things just fade away. And that is why I think my teacher's advice to me was actually very, very good, saying that the way to overcome stage fright is just to go on stage many times. The first few times you're just going to be very anxious and tripping over yourself, because you're not thinking about the dialogue, but rather, what am I going to do? What am I going to do? And you forget your dialogue, right? And so that happens. We actually have practice for that in our at Foothill College. If you enroll, and these are courses you can do, right? So take my advice, okay? These are, if you want to do many courses at Foothill, just to get credit, right? Just get units and credits and so on. Don't go for many hard courses. Maybe I said this to my 2C students, right? It's a mistake that students make, saying, I'm going to do all of the AP courses. I'm going to do all the honors courses. I'm going to do all of the hard courses. Okay, then you don't get enough time to do everything, and you do a mediocre job in everything. But however, there are lots of fun courses in all these colleges, right? Ceramics is a fun course. Although I'm saying it's a fun course, although it takes the same amount of time as programming. Okay, to get to be a really good potter, right? Or a ceramic artist like Andy in our in our ceramics department, you need to spend as much time as a rock star programmer spends coding, right? However, if you're doing ceramics to have fun, okay, you only have to do you don't have to get an A+, but you'll get a B or something, and you still have fun. Okay, and you'll get credits and units and so on. So those are courses that people in STEM should go and enroll in, right? And say, I'll get units, so I'll get my 12 units or 15 units or whatever is required, but I will focus on the hard courses in STEM, like calculus or multivariate variable calculus, or they take time. And the reason I say they take time is that in calculus, if you finish a chapter on integrating by parts or something like that, okay, and you go to the end, you'll see 500 problems. Well, maybe not 500 problems. I was looking through my son's text, a long time ago, right? And when I was working with him on the math homework and all, and then he goes to the end of the chapter and he says, these are, the teacher has marked these problems 1, 17, 18, 25, and so on. Those are the ones we have to solve. And so we solve that. And many people think that's all we need to do and move on. But, that's not true. Okay, the trick is to solve those problems. We shall give you the lay of the land, because the teacher has spent a lot of time looking through the problems and finding out which ones are sufficiently different to give you a picture of the entire landscape. But that means that you have to do these, so you have the bird's eye view of what this chapter is about. Now you have to go back to all of these. Number one, after 1, I told you to do 17, but you've done all of that. Now you have to do 1 to 16 also. And the reason you have to do all of the problems is just practice, right? That is like, saying I've thrown 1 part Andy on the wheel, so give me a pass. Yeah, okay, you'll get a pass. But if you want to get an A+, you got to throw 1,000,000 parts, right? Andy actually told us in our class. I did Andy's ceramics class at Foothill, right? And he told us when he was a student. Yeah, I think he was a student in Kansas or somewhere, right? He's from the South. And he said he used to spend nights, right? Many nights in the college studio, just making parts and destroying them, making parts, destroying them, just to get that perfect thing, right? And that only comes with practice. And that is the reason why we have so many problems in math books, right? So you have to work through all of them so that, integration by parts is not something that you would consciously think about and apply here. You look at it, you automatically know that's what you need to do, right? And that comes only with practice, just like music or anything, it just comes with practice. And programming is, once you got through all of the quests, it's not like you've done, right? So once you've done this, you have to work through all the sample problems in the loss of text, or loss of modules, or the text. You have a lot of examples. Work through the examples, and that basically builds practice. And obviously they have 500 problems, like in math now, right? You don't have to work through everyone. You will know, right? So that's the other thing, okay? Many students think that, well, I have to work through 500 problems. That's not feasible, okay? It's not like, when they put 500 problems at the end of a chapter, they don't expect, the author of the book does not expect that you solve all 500 problems, right? They put it there because you need to solve as many as it takes to get comfortable, right? Some people will get comfortable after 25 problems. Some people will get comfortable after 50, right? Nobody gets off. Yeah, I don't know anyone who's done all 500, but they all do many, right? Many people I know who are comfortable with math, computer science, they do many until you get comfortable. So you don't have to feel intimidated saying, oh, I don't have time to do all these things. You just say, well, I'm going to do as many as I can, right? So you keep writing these little programs, right? And maybe 5 of these questions involve for loops or different kinds of loops. And say, well, I've done this and I know how to do loops, and move on. That means you'll get stuck again. But you do all of the problems that involve five, not from the internet, because on the internet, there are many problems that not created by professional teachers. Okay, I think maybe, I don't know, right? Because they're all overlapping. Some these will be very similar and so on. Textbooks, right? That is why people pay money for textbooks, is because textbooks, they've done a lot of research into saying, very similar problems we shouldn't have in the exercises. We'll have sufficiently different problems, but also a rich set of problems. And that is why I go to textbooks or some source of material that gives you a varied list of numerous problems, programming problems. LeetCode, I wouldn't suggest. LeetCode is not a good way to practice for any of our 2A, 2B, 2C, 1A, 1B. It's good to have. Once you are good, LeetCode is good to have a good experience. You go there and say, hey, I'm going to do this. I'm going to try, and those are good to check yourself and do these things, or get practice and thinking on the spot in an interview and things like that. But really, textbooks are the way to prepare for textbooks and modules, right? For exams and midterms. I think you'll all have a great time, okay, in the midterm. Judging from what I've seen in class and your interest in the subject and the level of engagedness and all, I think you'll all have a good time in the midterm. They're not trick questions, okay. When I say trick, so some students have. So last quarter, one student said, I did this question in the midterm and it was tricky. I wish the questions were not tricky, right? Then I said, I thought there were no trick questions in the midterm. So I went back and looked. It wasn't actually a trick question, okay? It wasn't a trick question. It's just code that needs to be read carefully. That's all, okay? Because if you read, that's what it is. Even in professional programming, when you're out there and you're coding with your colleagues and friends, and code is not tricky, but it's just you have to look very carefully at what's going on, right? So, and it's just care and building care. Also, again, you say here's the other thing that could potentially trip you up. Say, well, you know what? I was so careful. I was painful. It was painful for me to look for 5 minutes in order to find that semicolon. Now I have this big program. Now you think I'm going to spend 5 minutes on each of these lines or each of these spaces? It's going to take me a horrendous amount of time if I'm going to take 5 minutes each time I look over the code. Doesn't happen. Okay, it takes 5 minutes the first time. It takes 4 minutes the second time. And so on. After a while, you'll find that it just comes automatically. So you won't spend that much time. So you have to get to the place, right? Get to the place where things come automatically. When it comes automatically, you can say, I'm done, right? I don't need to do any more problems. And so I think it's a good check mark, or not a check mark, a good milestone to have in your mind to say, how long do you need to practice anything, right? Whether it's music or programming or ceramics or any art, right? How long do you need to practice? And many people think, oh, I have a lot of practice to do. No, it's not a lot of practice. It's just enough practice to make sure that you are comfortable with it, and you'll know. You'll automatically, I think you know, right? So because I can say this because it's not just computer science. Many other things I've done too that take a lot of time and hard work. And I say, well, I'm never going to do this. I used to do that. I say that initially. But after a while, I find, no, actually, it's all easy, right? I thought it was hard, but it's actually easy. So you will know, everybody will know, right? Like my experience, okay? Everybody will know at some point that it wasn't hard. It was easy, and I just thought it was hard. Okay, so you need to get to that place, and you will get to that place. Just practice, okay? Practice gets you to that place. All right. So anyway, that's enough of a spiel for this morning, 8:32, and so let's start. Okay, if you have any questions. Also, if you don't want me in your face and you guys want to just talk amongst yourself and practice the coding, right? All right. So I'm happy to, right? Anything is okay. So let me know. If you have questions, please do ask. Don't ask in chat. Okay, there's one message in chat. I don't know what it is, but I don't read the chat message. Yeah. Okay. Okay, so yeah, please do bring up anything that you probably started preparing for your midterm already, right? Because if it's today, you probably read through the material, the modules or something like that. So you already have a few concepts that, maybe I should ask someone, or go to the STEM center, right? This is here. That is this is better than your STEM center, because I'm here and all of your classmates are here too. So if it doesn't work here, then you can take it to the STEM center. Because in the STEM center also, we have a lot of good, really good tutors. Lane Johnson, by the way, he's one of our tutors who's gone who knows the ins and outs of all of the quests all the way up to 2C, and he's one of our tutors too. And he's an incredible help. In fact, if you go to our Reddit, you'll see in the past, many of our students, your senior students, have written, praiseworthy things about Lane, right? So I say, hey, I went to the STEM center and thank you so much to Lane because he made me understand this. Okay, so that's all available to you. And right? We have free tutoring in the STEM center. And Eric, who's actually managing the STEM center for us too, he asked me to pass this message on. But he asked me at the beginning of the quarter, but I forgot to plug the STEM center and say, hey, you guys should be going to the STEM center and making use of these resources, because if right? So you just go to wisant.com or one of these sites and say, I want a CS tutor in my area, right? Wisant gives you tutors, right? You can pick any subject and go to Wisant. There are many sites, not just Wisant, okay? So you say, I want a tutor for history or something like that. And someone in the area, within your 50-mile radius or 10-mile radius, in Palo Alto, Fremont, San Jose, they'll connect you and say that person can give you a free lesson at a park, in a library. And you meet in the library with your notebook and your computer, and they give you this tutoring session, 1 hour, and you can see how much it costs. Okay, it costs about $80 or $90 for computer science. I don't know how much it costs for other subjects. Computer science costs $80. Okay, and many of these students, many of the tutors themselves are students. Okay, they're probably students at Berkeley or Foothill or Stanford or one of these places because they're in the area. And say, I'll tutor, right? In fact, you guys can do that too, right? Once you get to 2C, you can actually offer tutoring on these sites and say, I'm happy to tutor. These sites will take a cut. Okay, so they charge $80. Maybe you only get $60. But still, it's okay because it's a fun experience. Because by teaching other people, you also learn a new aspect of the thing. Hey, you know what? In order to explain it to this student, I had to approach it this way, right? And approaching it this way, I found something else in this thing that I didn't notice before, right? So it's another nugget that I can use to these things. So you can see, and STEM Center is free. It's free, right? But it's free to you. However, it still costs $80 or $90 per hour for, or something like that for the tutors, but that money is being paid by the taxpayer. Okay, so essentially, if you're not making use of these facilities, well, not just Foothill, right? So, for example, Namrata is at a UC. I think some of you are in UCs too. You have tutoring services. Actually, cost a lot of money, right? And you get it for free. Your TAs and RAs are being paid good money by the state, by the college. And so by not making use of it, it's like saying, I'm going to go to a restaurant. I'm going to have, I'm going to pay them like $500 for an incredible meal, but I'm not going to eat anything. I'll just come out and say, hi guys, it was great. Great spread you got here. Here's $500. All right. So no, that's not the reason we go to a restaurant, right? So you got it. So make use of these things rather than because, and especially your age group, right? Because there's a lot of competition. You have Netflix, you have Amazon Prime, you have Hulu, you have Fortnite and all these other games. And, so there's a lot of other competition, but you always have to, I think, right? Look at the costs of these things, right? So you say, hey, you know what? That one I can get for free anytime, right? A game of Fortnite I can get for free anytime. I can play. I can call up my friends on a Saturday night and we can game. But I can't do this with a tutor. So and that is only available for a limited time. So I got to take it when I have it. So so you got to prioritize things like that. Okay. All right. So what would you like to do? Should we just pick up Sabrina's code and have a game first? Break the ice and then go from there. You can also we can look at the code, that we wrote, Sabrina wrote last class. We can look at the code and then you can say, hey, I don't understand that part. I don't understand that part. And then I can, in fact, doesn't even have to be me. One of you can also say, hey, I know how that works. I'll let me take a crack at explaining that to my classmates. That's the best way to actually seal in the knowledge for your own midterm experience, by explaining it to a fellow classmate. In fact, I would recommend that highly anytime, because it's online and you're all in different places. Some of you are at home and some of you are at work. It's harder to link up. But if it was a face-to-face class, or most of you are on campus, I would actually recommend that you guys pair up, okay? Pair up or get into groups of 3 or 4 people, and then one person says, "I'll explain this concept to you too. You explain that concept to us too," and right. So you just separate, share the things and then explain to each other. And explaining each other is not just beneficial to the parties that are being explained to, it's hugely beneficial also to the explainer. So all 3 people will end up, benefited from that exercise. So if at all you're able to, just pair up with other people, even on Zoom, right? Even on Zoom, you can just say, hey, I know you're on the same kind of quest or same kind of thing. Can we just do a Zoom session? I'm trying to understand this. I'm trying to put together a group. Maybe you can put together a group, right? So find a time. You can use Reddit if you want, even our Reddit, and say, hey, I'm trying to put together a study group. Anybody interested? You use a Foothill flag. Right? Anybody interested in doing a study group on Saturday at 6 p.m. right here? Or you can do a Reddit poll and say, I'm interested in doing a study group. If you want to sign up, please pick a time, right? And we'll pick the most highly voted time and say, all right, that time you create a Zoom link. It's free, okay? You can create Zoom links, and Zoom is free for up to 50 participants, I think. Yeah, so you can create a Zoom link and have a session with your classmates and work through issues on Zoom. And if you're stuck at the end of these, if none of the people in the group can figure something out, you can absolutely reach out to me, and I'm happy to do a separate quick Zoom session later on. May not be the exact same time, because the time that you guys decide may not work for me, but it may work. I don't know. I can all say, well, make another time. I'll come and we can work through an example for that. So all of that is possible. How about that? Okay, so if nobody has any ideas, we'll just pick up Sabrina's code. Someone should take the opportunity to, in fact, maybe we even end up coding. So maybe one of you guys, right? Maybe Antonio, who else? Ryan, Antonio. I saw a couple more people here who haven't coded. Hey, Minghua, I don't remember you coding. You were, yeah, Minghua, you haven't coded. So all right, so anyone who hasn't coded before should just pick up the screen. Let's say the first person to pick up the screen gets it. Okay, pick up the screen and click on the link that Sabrina shared, and then and fork it, and fork the code so that it becomes your own code. Then we can start running it, And then as it runs, we can also look at, hey, this is what, and in fact, we won't look at the code, we'll look at the experience and say, and in the experience, we can ask questions like, hey, what part of the code finds out how fast these runners run? And then we can look at that and say, hey, that's how we determine how fast the runners run. Or what part of the code writes, draws these people coming close to each other. Okay, and we can look at that too. And that way we'll also nail down some of the concepts that we've covered in the past.
I had
that?
a question.
Yeah, Erica, go ahead.
So I like on the midterm, I know we're not going to be graded on like syntax errors, right? Because that syntax is a style. Is that?
No, syntax is not style. Okay,
Okay,
so you may get syntax related questions. You could say you may get a question saying, is actually very few, maybe none of them, but I'm thinking it's fair game. Okay, maybe I'll introduce some syntax related
like
questions
on the
later on.
because on the midterm, like there were like compiler errors and like the logic errors, and like I know syntax is an error too.
Oh, compiler errors are syntax errors.
Oh, okay. Oh, okay. So compiler versus logic, I guess, are the two main groups of errors. Yeah, because I know why things will error out, but I wasn't really like categorizing them as in my head.
Yeah. Here's a good way to know what is a syntax. So here's what happens. Okay, your program, when you write a program, well, actually, you know what, I remember. So I remember we never actually talked about what happens in the background when you call a function. We can talk about that today. Yeah. We can talk about that today. Okay, we can talk about that today because it's really interesting and juicy. Okay, so we can talk about that today. But however, so when you write a program, the program, first of all, if it needs to be converted to machine code and given to the CPU, it should be grammatical, right? You can write some program that it's not even in C++ and ask a C++ compiler to compile it, right? So it should follow a grammar. Like if I'm talking to you guys, I got to talk in English. I have to use the right parts of speech and so on and so forth. So I have to use the right English grammar to talk to you guys. Just like that, when you're talking to the compiler, ask the CPU to do something. First of all, it needs to be in the right grammar, and the grammar it can be a full-fledged language like English, because English is designed for a more sophisticated computer in our heads. It can handle a lot more uncertainty. It can do disambiguation, and it can also fetch probabilistic data and things like that. Okay, so that is not built into a compiler. So a compiler, it can't handle a huge language like a human language, but it can handle a much smaller language. That smaller language is our programming language. That's why C++, Java, Python, so much simpler than English, right? So if people who think that I can't learn a programming language, you got to ask them, you think you can learn a programming language? You just spoke to me in English. No, you just spoke to me in Chinese, right? These languages are like a million times harder to understand and use than C++. Really, that is true, okay? But you've mastered that. You're all talking perfectly fine to your friends and neighbors and family. That means you've already mastered a language that is far more complex than C++. So it's just that you just have to say, well, you know what I know already from using a complex language, I'm just going to take it and remove a lot of stuff. I only have to learn the small part. That is your programming language. So what happens is that the compiler checks the programming language for grammar. Okay, and that grammar. Another name for grammar is syntax. Grammar and syntax are the same. So, if a compiler results in creates an error, flags your code for error, that is called a syntax error. Now, after it's compiled, it's got it says there's 5 modules. Let's say this module is responsible for moving a character on a screen. Okay, this module is responsible for determining the speed of the character and the direction and so on and so forth. This is more common, more logic here, and they're different programmers, right? So because the logic for creating characters on screen and moving things around, maybe that's given to a programmer who is more artistically minded or has a different skill set. They all know basic computer science, but after a while, you say that. So they're all, and this is developed by someone who has deep understanding of data structures. The module that controls their movement. Okay, so they're 2 different people, but so the compiler will say, well, that person's code is all perfect, no grammatical errors, no syntax errors. This person's right now. That is not the end of the job for the system, right? So the compilation process is 2 steps. The first is actually the compilation, and the second is a linking together of different parts that were all being compiled, meaning checked by the compiler, saying they're all grammatically correct. Now you need to link them together, saying, Omar called a function called move, determine distance to move this player, okay? But that wasn't coded by this person. That was coded by some other person, maybe in a different country, maybe in Africa or somewhere, right? So different country, they coded it, and you got the code from that person, and it's out there. So this will. How do you link these two together? So that is a function of another program. They're all bundled together. Today we use these programs. Back in the day, when I first learned to program, I think there were two separate programs. One was called the compiler, and the other was called the linker or loader. Okay, they're two different programs. So we would first compile the code, turn it into something called object code, which means that the compiler has looked at it grammatically, right? I'm going to convert all of your instructions into machine code, all binary. Humans can't read it anymore. So they're all binary modules. Now the loader, I have to call as a programmer. I have to say, I have all these object files, .o files. Now I need to link them together, saying Omar's function calls need to be linked with Erica's code or something like that, right? So the linker needs to come in at that point and say, basically, I say, loader, here are all the object files, link them together and create a single executable file. So that's where the loader comes into the picture and says, I'm going to take this code and make all these links. And that is where you'll see another kind of error. That is not a syntax error, but it's actually a linker time error. There's a name for it. I forget the name, but you'll see these names, right, when you code. Unresolved externals. Okay, resolution. It is called unresolved externals. Okay, in an IDE, that the error that you will see is called an unresolved external. What does it mean, right? So Omar wrote, let's say, the graphic part of the application, right? So that's all functioning really nicely if it got the distances correctly, okay? So and when he's writing the graphics capabilities of the game, what Omar will tend to do is, in order to test these out, I need to have some values coming in for distance, okay? However, the distance calculation involves complex data structure manipulation that I'm not going to do, someone else is going to do. So what I'm going to do is going to create a make-believe substitute for that function that Erica is going to give me 50 days later, okay? Or 3 weeks later, Erica is going to develop that and give it to me. But I can't wait for 3 weeks to do my stuff. So I'm going to create a dummy version of a make-believe Erica function, right? As I says, just return 5, right? Whatever the distance is, just return 5. That you can write, anybody can write, right? That is called a stub. Okay, that's a stub. And Omar will create his code for the graphic part using stubs for every function that he is eventually going to call someone else's code for. Does it make sense? That way, Omar will be able to test the whole thing because the UI is the whole thing, right? Not the whole, UI is what he is testing, right? So he'll be able to test it by using fictional values, fictitious values for all these, right? Now, however, here's the thing, okay? However, imagine that Omar's code had called Erica A, Erica B, Erica C, right? So 3 functions. But Erica didn't know that she had to implement C, and she only had A and B, right? And so she implemented those 2 functions. So now the compiler would have looked at Omar's code and said, yeah, fine, good to go, right? Looked at Erica's code and said, that's good to go too, right? Because there's no errors. However, the linker, when it tries to join them together, will say, hey, you know what? Omar wants A, B, and C, but Erica only gave A and B, right? And so the linker will now produce a red ink message. I don't know if it's in red ink, right? In most IDEs, it'll say unresolved external, okay? C is a function that Omar called. It's an external function because it's not internal to Omar's code. It's an external function, but I can't resolve it because I can't find it anywhere. Yeah, that is called an unresolved external. That is not a syntax error, okay? That is a loader error. That's a linker error. So, but you'll know, right? So compiler errors, usually syntax errors, some missing semicolons and things like that, braces. So those are syntax errors. Anyway, I can talk about what happens in a function, right? When a function is called, can I talk about, because we've used functions now, right? We've used functions a bunch of times already, so we know how to use functions. So I can talk about what happens when you call a function. Okay, everybody okay with that? Yeah. Okay. All right. Well, Erica's the only one who says yes. Other people have questions or something else that you want to talk about? Raise your hand if you want to just learn about what happens in the background when a function is called, right? It's not going to be directly tested in the midterm. So if you do have questions about the midterm, we can do that. I can still have time next week to talk about functions, but otherwise I'll talk about it now. Want me to talk about it now? It's 5 or 10 minutes, that's all. Yeah, okay. All right. Well, anyway, Namrata's nodding her head and Erica raised her hand. So, all right. Okay, so when so all right, let me start from computer architecture, right? Now, I'm not going to start all the way in computer architecture. So when your program is compiled, turned into instructions for the CPU, right? The CPU, humans can't read it anymore, but the CPU can read each line, each byte is one instruction, or each, depending on the length of the instruction, right? Each byte or bytes instruction, they're going to read the instruction, execute it, move on to the next one. So your CPU, if you break open the chip, right, the CPU chip inside your computer and look inside it, you'll see different parts inside of the CPU, right? Well, technically you can't see, obviously, but abstract. So you can, there's different parts. One of them is called the instruction pointer. I think is it the instruction pointer or program counter, something like that, okay? Instruction pointer. And the other part, I think that, I don't know, I have actually forgotten the names for these different slots inside, right? There's registers where you keep temporary values. I think it's called the accumulator. Or there's a place where you put the instruction. Okay, so your program, after everything has been compiled and linked together, is created, is put inside a single binary file. It's called a binary file. Now, when you say binary file, people always say, oh, binary is bits and bytes. Well, in a manner of speaking, that's what it is, because it's all bits and bytes. Humans can't read it anymore, but it's not like a data representation kind of binary. Binary is another name that programmers use to talk about compiled and linked programs, even compiled programs, right? Which humans can't read anymore. It's in binary, meaning the CPU can understand it, but you can't understand it anymore. That's what it is, all right? So now your program has been converted into a series of steps in binary. Now, after compiling it, is your program running immediately? No, it doesn't run, right? After you compile it, it's just stored in a file. So I've got a bunch of bytes that represent, let's say, Antonio's program, okay? And the compiler says, no, Antonio wrote this program, I converted that into bytes, and that's Antonio's program from here to here, right? So now all these bytes are Antonio's programs. It won't run it immediately. The compiler will say, I'm going to create a file called antonio.exe or a.io or one of these files, inside of which it'll load all those bytes. It'll put the bytes in a file and store it just like another text file. So you have a .cpp file, which has your CPP file that you can read. The compiler will create another file called a .exe file or an executable file or a binary file, inside of which the exact same program exists. Two programs, they're both exactly the same, except that one program can be read by you and not the CPU. The other is just the same program in a different language. The compiler translates your program from human language to CPU language. That's all. It's basically a different language. So your program is basically a sequence of bytes that is stored on the hard disk. Okay, it's on the hard disk. Now, if you want to run the program, it's technically, theoretically, I shouldn't even say technically. Theoretically, it is possible to just run the program off the hard disk, meaning that your CPU could say, what is the first instruction to run? Oh, let me go to the hard disk where the program is stored, and I look at the first byte of the program. That's my first instruction. Okay, second byte. And so the CPU could basically step through the program on the disk itself and run it. However, that'll be really slow. Yes, because technically you don't really need to run things fast to prove that it actually works, because the abstract model of a computer, it's called a Turing machine, right? The Turing machine is the abstract model of a computer, meaning imagine that you have an infinite resources. Can you do this with a computer or not? That's the question the Turing machine tries to answer, right? So it's not a real machine. It's just an abstract machine, a theoretical thing. And it's basically just your entire program is a series of, I don't know, was it ones and zeros, dots and dashes on a long piece of tape. Okay, and then the way the machine, the abstract machine, not a real machine, your fictitious machine works is basically just has a scanner head, and it'll look at the paper right underneath and say, is that a 1 or a 0? Okay, and then it has maintained state, and then it'll say, all right, if it's a 1, I'm going to move to the left and read the next symbol. If it is a 0, I'm going to move to the right, and things like that. Okay, it makes these decisions. So that's exactly what a CPU will also do. Except it does it a whole lot faster because it doesn't have these moving mechanical parts in there. It's all being done at the electronic level. So a computer is essentially a Turing machine. It's a blindingly fast Turing machine. That's all. Okay, so what that means is that when you go on to study, later on in grad school, when you go on to study the theory of computation, right? This is what you learn. What is actually computable? What is not computable? That's a very interesting question, isn't it? Because what you're asking there is not whether, here's a problem, can today's computers solve it? Okay, it is actually mind-boggling to ponder this. And if you're planning to do research and all, it's very interesting. Okay, so the question we're asking is it computable or not? We're not asking, is it possible to be computed using today's computers? In fact, we're not even asking, is it possible to be computed using a super duper powerful computer that humanity will construct after 5 billion years? All right, like deep thought, right? It's like the Hitchhiker's Guide to the Galaxy, right? So you say 5 billion years later, humans are going to be so much more intelligent. They have so much more resources. They'll build a computer. Can that computer solve this problem? Okay, even that you're not asking that question. Is that thing computable or not? You're actually saying, can it be solved by any computer, whether it's human or aliens, right? Some super duper supernatural power built that computer in a traditional computer, right? But can that solve it? That is the question. That is it computable or not? And so, and then the marvelous thing is that you can actually show that there are certain problems that no matter how sophisticated the computer is, no matter, right? No matter at all, there is no computer on Earth, anywhere in the universe that can solve this problem. Okay, and so that is a non-computable problem. And so there's families of these problems that you'll encounter later on. Say, oh, there's a whole family of non-computable problems. These things cannot be computed at all using traditional model of computing, right? Maybe you can solve that using non-traditional models of computing, using quantum computing and things like that, or new paradigms that may emerge. But you can't solve that using the von Neumann architecture, a traditional model of computing. So those are kinds of questions you'll ask, right? Anyway, so what happens is that the program is on disk. When the user says, I want to run that program. Let's say Antonio's program is called Blackjack, right? So maybe he wrote a Blackjack program, and so and then Ryan wants to run Blackjack, Antonio's Blackjack program one day. So he just types on the command line. By the way, most of us are just used to GUIs, right? So just double click and run the program. But when you double click, it's just eye candy. What happens is that when the double click will get translated by the GUI into a command line execution, essentially, right? Meaning that program is loaded and so on. So what happens is that when Ryan says, run this program, double click on Antonio's Blackjack program, the operating system, whether it's Mac or Windows or Linux or whatever it is, you're running an operating system, right? When you open up your computer, you're talking to the operating system on the shell. So that program will now take Antonio's compiled Blackjack program, which is on disk, and say that because it's so slow to run it on disk, it's going to take everything and load it into memory. Okay, memory is RAM. Our computers have 8 gigabytes, 64 gigabytes, lots of memory. It'll load that program somewhere in memory, in contiguous memory locations. So maybe from memory location 5000 to 5055, right? 55 byte program. So it'll just load everything in memory. Now, at that point, the program is ready to be run by the CPU, right? Until then, it's not ready to be run, because you can't tell the CPU, hey, I got a program on disk, go and run it on disk. Then it'll say, oh, I can run it, but it'll take me a few million years to run, because there's all the mechanical motion. However, when you put it in memory, the operating system will take the program, the bytes, and put it in memory. Now we can signal the CPU saying, CPU, Mr. CPU, there is a program that I loaded up in memory. It starts at location 5037, right? 5037 is the first byte, which has your very first instruction. That is where your main, right? In C++, you say all programs start with main, and you have to have a main. Main is the entry point of the program, meaning that is where the compiler will tell will put instructions, right? The compiler, the loader and everything, when your final program is stitched together for the CPU to run, it'll say this is the entry point of the program, meaning that is the first. Then the operating system says, go to this is the entry point. Your entry point is at byte number 5037. Start running from there. Okay. That much is freebie. Okay. It's given to you already. You don't have to do anything, right? So you've written the program and it's done. Now, at that point, the CPU is, it's wired. That logic is actually wired into the CPU. It'll take that instruction that is at byte number 5037 and copy that into a special location inside the CPU. I think it's called the accumulator, right? Yeah, those of you who are doing, computer architecture may not know the exact name. So it'll put it there and then ask the CPU, interpret that, right? And the CPU already knows what each of the different bit patterns mean. So it'll know, right? Hey, that pattern which came from there says add 2 locations, add whatever is in register A and register B and put it in register C, put the result in register C, something like that, right? Or multiply them, or move something from that part of memory to this part of memory. All of those are different instructions. So the CPU will read the byte that is being loaded into that accumulator and say, that's what I need to do. And it'll then execute that. It'll do what that thing says, because the CPU is only capable of doing a limited number of things, right? Maybe 5,000 things or 500 things or something like that, right? So depending on the number of instructions. So each instruction plus its variations, those are the only things the CPU can do. So it'll, because it's all wired into the CPU, it knows exactly what to do, right? So because that part is not coded by us. So it'll execute that. It'll take that instruction, execute that, and then automatically, this is also built in into the chip, right? It says 5,037 fetched from memory, interpreted, executed. I'm done with it. The next thing I need to do is go to 5,038 because the next instruction is in the next subsequent byte. So what it has another inside of the CPU. There's another small place which stores the location where the next instruction should come from. Okay, so when the CPU is initially fired up with Antonio's program, the operating system essentially loads 5,037 into this special register called the instruction pointer. I think some people call it program counter. The instruction pointer. The instruction pointer essentially points into memory, saying that's where your instruction is. That's the next instruction to execute, right? So, and that is what the CPU does: fetch, fetch, execute. This is 3 steps I forgot, right? So it'll fetch it, interpret it, execute it, and then increment the program counter. Okay, important step, increment. So that means if the value 5,037 was loaded in the CPU very first time, after fetching and executing the instruction at 5,037, the CPU will automatically increment the instruction pointer. It is not 5,037 anymore, it's 5,038. So the next clock cycle that happens, it'll look at that and it won't see 5,037, it'll see 5,038. So the next instruction it's going to fetch is the next instruction. And that is a cycle. It happens repeatedly until there's a special instruction in Antonio's code that says return 0, which gets translated into stop or exit, right? That's also a single byte instruction. So until it encounters the stop or exit instruction, it's going to keep doing that in a loop. Fetch, interpret, execute. Fetch, interpret, execute. Well, actually, increment the program counter. Okay, and it'll do that in a loop until all of the instructions one after another have been executed. Okay, so far, that's the simple explanation of how a program without functions behaves, right? Now we're going to talk about what happens when you have functions in the code, okay? Because a function, meaning that when you write a program with functions, when you write one program with it's all main, okay, one program, you can think about it as, all of the instructions from 5,037 to 6,025. They need to be executed in sequence, one after another. Yeah, because it's just one, no functions at all, one big program. Okay. However, when you write programs using functions, you may have chunks of code that say, from 5,037 to 5,095 is one function, and then maybe 6,012 to 6,014 another function, and so on and so forth. Right. So you have different functions everywhere, and then the first function that is called by the operating system may not do the entire job, but you have to do this. But then at some point, it's going to say, well, you know what, at this point, I can't do the next step. However, I need to do something that is contained in another function, which is not in the next memory location, it's somewhere else. So it has to execute instruction. So it's executing 5,037, 5,038, 5,039. 5,039, it may be a function call. That means the next instruction to execute is not 5,040, it is 6,025. So if the CPU does its usual thing of just incrementing the program counter, it's stuffed, isn't it? Because it doesn't know that, oh, you know what, this is a function call, I need to go there. I can't be executing in a sequence anymore. So at that point, control has to be transferred completely. The instruction pointer needs to change. Yes? So at that point, the instruction pointer after 5037 won't be, 5000 after 5039 won't be 5040, but it'll actually be 6025. That instruction pointer has been changed. So that is how it leaves the current function and starts executing instructions somewhere else in memory. That is your function code. Now, that presents, right? So far, is it okay? There's only 2 more things we need to cover about how the function execution happens. Okay, if you're comfortable with this, I'll explain the next part that is also interesting. And what everybody okay with this so far? This is how transfer of control happens, right? Executing one after another. That is the default behavior. The CPU always executes one instruction after another in sequential order, except when there's a function call. Well, yeah, except when there's an exit instruction, right? An exit instruction says, that's it, I'm done. I'm going to give control back to the user. Forget about that. It's a function call. It cannot do the next instruction. It has to do something else somewhere out there. Okay. So now when it goes there, it's going to start executing at 6025, 6026, and so on and so forth. When that function is done, saying, okay, I'm done, you can go back to where you came from. How does it know where to go? Because you started off at 5025, right? Or 37, 38, 39, 40, right? But instead of going to 40, it just overrode the instruction pointer. It went somewhere else in memory and it started executing there. When that is done, how does it know to go back to 5040? Right? So here, it's interesting, isn't it? Because this 5040 is what is called the return address. Okay, the return address is the place where you should come after doing your job, right? So you're doing something, and at this point, you say, well, you got to go there and do something. But after you're done, come back to this place. So that 5040 is called the return address. And where would you store this? Where would you store that return address? You can't store it in the CPU, because the CPU can say, well, I got a place where you can put all the return addresses, right? No, it doesn't work. What happens if that function calls another function? And then, that function has to return and then come back, not to this function, but has to go to that function. Yeah? Yes or no? Maybe that part is confusing, right? So let's say, oh yeah, okay, all right. So yeah, all right. So yeah, right. Well, I don't know. That'll take too much time to. It's a little, humorous thing, but it will take time to explain, right? Yeah, to get into. So A calls B, right? A is what Antonio wrote. Now Antonio calls a function called B. Now when B is done, it needs to come back to A. Yes. However, B calls a function C, right? So when C is done, should it come back to A or B?
I'm thinking B, but I'm
Yes.
not sure. Yeah.
It has to come back to B. Yes. It has to come back to B, right? It has to. Because I'm baking a cake, and let's say I ran out of sugar. So I told my friend, oh, we need to get some sugar. Can you go run to Trader Joe's and get some sugar, right? And then she goes off to Trader Joe's, and then on the way, she figures that her car needs gas or something like that, and says, hey, can you fill up my car? Right? Someone else does that. But when that is done, that task needs to return to my friend, not to me, and say, yeah, I don't know. It's easy to visualize, right? So each function, when it calls another function, needs to get control back from that function when it's called. You can, right? So that is called a last in, first out order of execution. Meaning the last function to be called is the first function to be exited, right? So A calls B, B calls C, right? And so on. And when C is done, it goes back to B. It doesn't go to A. So if you have like 1,000 function calls chain one after another, right? You can't have space in the CPU for storing all of the return addresses and the order in which they have to be. It's a pain, right? We have a brilliant data structure which you will actually implement in quest number 8. You will implement in blue, right? In blue quest number 8, you're going to implement something called a stack. Okay, a stack is a first in, last out data structure, okay, or last in, first out data structure. It's called LIFO. And you can Google for LIFO. It's called last in, first out. And what that means is that it is just an array. In fact, an array is in fact the most powerful data structure you can encounter in computer science. An array can do incredible things. Most of the more sophisticated data structures we get are taking the array and hiding some of the power of the array. That's what it is, right? So you take something really, really powerful and give it to a user and say, well, it's really powerful. It could basically blow up in your face. So I'm going to cover up all the dangerous parts so you don't access the dangerous parts. Yes. That's essentially what it is. A stack is you can think of the stack as an array which has dangerous parts masked away so that you're only able to do a limited set of operations on the array. All right. And the limited set of operations that the stack provides you is you can give me an item and I'll put it on the bottom of the array. But if you want to take something out, you can take any arbitrary item out. You can only get the last item that's on top of the array. It's like a stack of plates, right? You get a plate, you put it, you keep stacking plates, at the end of a party, and you got to load the dishwasher. The last plate on top is the first one to go into the dishwasher. Yeah, you can pull out plates from the bottom, and that'll crash the whole pile. So the last one in is the first one out. And the data, and you can take an array, and that's what you're going to be doing in quest number 8. You're going to take an array and make it behave like a stack. Meaning that, it's a really powerful thing. I'm not going to let people access anything they want in this array. I'm going to make them access only the tip of the array, which means only the exposed part, which is the bottom part or the top part, depending on how you structure your stack. That's the only thing, which means you can put something there. But as soon as you put something there, the item that was previously on top is not the top anymore. So which means it can't be accessed anymore until this one is gone. Yeah, so a stack data structure gives you that functionality. And so when you run a program and call a function, that's exactly what happens. So your program gets given what is called a runtime stack by the operating system, whether it's Windows or Microsoft, or Linux or Mac or whatever it is. When you run a program, you'll get given a runtime stack. It's called a runtime stack. Right? It's called a runtime stack because in your programs, you'll be creating your own stacks for doing various things. Right. So many in CS2B and 2C, you'll be creating stacks of your own for using in a particular algorithm. You want to distinguish that from the system stack, your program's runtime stack, right? So the CPU says, I'm going to create my own stack. I'm going to call it the runtime stack, and you won't see it. The programmers cannot see the runtime stack, but it's there, right? But the CPU knows where it is, and every time it has a return address, it'll push that on that stack. How cool is that? Okay, meaning that stack can keep on growing, but it also maintains the last in first out property, so that if A calls B, A's return address is pushed on the stack. Now B calls C, now B return address is pushed on the stack on top of A. Now there's no way you can go back to A until you pop B off, yes? Because B is now on top. So you can do that any number of times. Any number of function calls can happen one after another. Only the last one has a return address right on top, and that needs to be popped. So the stack will hold the return address of the place where you need to come back to, so that when that function, when Antonio called that function, right? So when that function is done executing, it can now pop things from the stack and say, well, you know what? I'm done. Now let me see what my return address is by popping the return address on the stack. It'll take that and say, hey, I need to go back to 5040, okay? Because my stack's at 5040, it'll come back there. That is how the return loop works in a function call. However, that's not enough, right? So far is it just one more, okay? And then we're good. So far is it okay to the visualization of that entire loop, where call a function and return address and how a function goes back and all. That's how it happens. Okay. The other thing we need to know is how are parameters passed to functions. So you might say, in Antonio's program, you might say, well, I need to call a function to find out how many cards are left on the, I don't know, it's just blackjack, number of cards matter in blackjack. Right. So let's say there's a game, right? So he wants to know how many functions. So he calls another function, and that function is. But however, maybe he needs to say, I not only need to know how many cards are on the in the pile on the table. I also need to know how many cards are there, given that the top card was a black card. Okay, so maybe he has a game in which that matters. So he'll say to that function, here, the top card is a black card. Now tell me what my number is. Or the top card is a red card. What is my number? Okay, so he's passing some information, and that function needs to use that information and return this. So how does that happen? How does that function get this information? Because it gets that information because in the process of calling that function, the caller is not only going to push on the stack the return address where that person needs to come back after you're done with the job, but it also pushes all the parameters. Okay, so it says before you start your job, function number B, right? Function B, before you start your job, make note of this. I push the place where you need to return after you're done on the stack. On top of that, I also pushed all the parameters, right? So the stack, before function B is called, the stack has the return address, but it also has all the parameters in there, one after another, right? So now when that function starts up, when B starts up, you can now say, right, I need 3 parameters to function properly. I need a double, I need a string, and I need a character. Okay, so it'll say, so therefore it'll pop from the stack. It'll pop 8 bytes, right? A byte is 8, a double is 8 bytes long. So it'll pop 8 bytes off the stack and say, well, that is my double. Then it'll pop, I don't know, 24 bytes for a string, right? So and say, hey, that is my string. And then it'll pop these things in a measured way. It is like super duper important. It has to pop them in a measured way because it needs to know that the first 2 bytes that I need to pop or my first byte is a character. And after that, I have 8 bytes. That's double. And after that, I have 24 bytes. It needs to do that in a specific order. If it gets it all mixed up, the program is screwed, isn't it? Because, I have my string here, a double and an integer, but that program popped them in a different way. It tried to get an integer first and then a string and then a double. Okay, then it's all messed up because the bytes are all mixed up now, isn't it? You got to get them in the exact same order in which they were pushed. Otherwise, the values will all be mixed up, right? Not even mixed up. It'll be garbage because 2 bytes of the integer broken up into 1 in a character, and the remaining byte is part of the next string. So it's all garbage and junk after that. Okay, so it needs to be popped in the exact same order. And so all the parameters are all pushed on the stack also. Now, this is why function declarations are so important, so super duper important in all languages, in C++ especially, because I think in some other languages, the compiler does multiple passes of the code. So it actually, the first time it'll look at all the functions and say, well, these are the signatures, right? I know what the declarations are, how many bytes, and so on and so forth. In C++, the compilation process is also really fast. It just goes right through the code and says, do I know that function? Do I know that function? Do I know that function? And if it knows the function, it knows how many bytes will be popped on either side and pushed and popped on either side. The mismatch is if for instance, you said, I'm going to write a function that takes an integer and a double, okay? And so it's 2 bytes. You're going to push 4 bytes for the integer and then 8 bytes for a double in that order, right? But that function, let's say someone else wrote that function, maybe in a different country, right? Maybe they were in Egypt or somewhere, and they wrote they wrote this and they wrote that method, and there was poor communication between team members. And that person, instead, the logic was right. However, they said my function takes 2 parameters. It's a double and an integer, right? You, however, thought I'm going to call that function. I'm going to pass it an integer and a double. Okay, same number of bytes, right? This is 4 plus 8, 12 bytes. They're also expecting 12 bytes. So they'll pop 12 bytes. However, right, their data is going to be screwed, isn't it? Because you pushed 8 bytes. That's your, those 8 bytes are your double, and your 4 bytes are your integer. That's the order in which you create the stack. You push things on the stack, but that guy is going to pop that and this, right? So the first 4 bytes of your double are being interpreted as your integer, or something like that. So it's all mixed up, right? Bytes are all mixed up now. So that is why the declarations have to match, and the compiler red flags. When you say, hey, you know what, this function, you said it takes an integer and a double, but you're calling it with a double and an integer, and the compiler will flag it for you. That's because the compiler has your back and say, you know what, if you compile this code and I let you and I let it squeak through, right, without having a back, then the CPU, when it runs it, it's going to fall apart, right? It'll crash because it doesn't have the right information, and who knows what's going to happen after that. So I'm going to have you back and make sure, because I know that function takes parameters in that particular order, this is the way in which you should call that function. If you call it in a different way, I'll say, I don't know that function, right? So I think we've encountered this error in class code in the past, saying we wrote something and then we compiled it, and then the compiler says, I don't know, unresolved external, I don't know where this function is. But you can see that function, it's right there. And the reason the compiler doesn't see that function is because you call that function with a different order of parameters than the function was declared, right? So when you say, let's say, give it a name, right? Count cards. There's a function called count cards. Okay. So if there's a function called count cards, you call that function, and you gave it some parameters. And I don't know where I was going back. Anyway, it'll come back to me. Right. So, so basically, the ordering has to be the same, and so that is why in your declaration, the function declaration, you actually have to say, right, up at the top of your file, in your header files, for example, you'll say, in my code, I'm going to be calling a function called count cards, and it takes two parameters. And the first parameter is an integer, and the second parameter is a double. You actually say that, and a semicolon after that. The declaration is for the compiler to say, all right, when that guy calls this function, I'll make sure that it matches the exact order in which the declaration says the function should be called. Does that all make sense? Okay, so now that is the reason why we have these, conflicts, and many times in not so much in 2B, 2A, some students in later requests have made posts in the past saying, hey, I'm calling this function and I've written this function, but the compiler is complaining, saying that it can't find the function. Why? It cannot find the function because a function that takes an same name function, count cards, okay, count cards, same name, count cards, that's also count cards. Count cards were written by some person in Egypt, and it takes an integer first and a double next. Okay, you're calling count cards, you're passing it a double first and an integer next. So obviously it is a function, but it's not that function, because that function takes a double first and an integer next, right? But you're calling a function which takes an integer first and a double next. Therefore, I'm hoping that someone else would have written that function, right? So that's what the compiler says, right? And so when you submit that code, it'll say, count cards, unresolved external. I don't know where that function is. But you look at the code and say, no, it's right there. The compiler can't find it. It's right there. I can see it right in front of my eyes. But that's because you look at it carefully, you'll see that, I called it with a different signature than it was declared. That's why the compiler couldn't see it. Does that make sense? And so all of this reading and all of the warnings and errors from the compiler, they're there for our benefit. Okay, if the warnings weren't there, the programs will do crazy things and we can't figure out what the hell is going on, and there's lots of errors. And to prevent that from happening, in order for you to have a good experience running the program, that is why the compiler says we'll just make sure everything is squeaky clean before your program starts running. That is why we have all these errors. So we should never complain. We should never complain at the compiler saying, oh, I'm going to run the compiler and it's going to spit out a lot of errors. Damn compiler. No, it's a good compiler, okay? Saying, I got your back, don't worry, okay? I'll take all the flack and make sure that your program is squeaky clean before you go out there and work. Like college courses, right? So the professors will say, round out the rough edges in students so that when people start employing them, say, hey, these students are really, really good, right? They're top students out there. That's because they've had a lot of chance in college to make all the errors that they ever want to do in their life. Okay, make all the mistakes you want to do later on in life, make them in college. All right, so where you have the chance and the backing and the safety to do it, and so the compiler takes care of that for you, so that when it's out there in the wild, it'll behave correctly, and people will say, hey, what a great program, right? It does things and never craps out, and that's because the compiler took care of it for you. Does that all make sense? That is the entire life cycle of a function call. So when you write a function, it's stored on disk, it's then translated into machine code, stored on disk, and then when you run it, the operating system, Windows or Mac, right, Mac OS, right, Mac OS, will take the contents of the disk, load it into memory, and then signal the CPU saying, this program I just loaded into memory starts at that memory location, start, okay? And from that moment onwards, the CPU will immediately pick up and say, I'm going to run one after another, bam, 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 bam. Oh, there's a function call. Okay, where am I at right now? This location? Okay, let me take that location, store it on the stack, and then I'll tell that function to take over. Okay, that function does it. And after it's done its job, it'll say, I'm done my job. Then we'll pick it up from the stack. Oh, that's where I need to go back. We'll go back and we'll resume execution. Does that all make sense now? That is the background, right? Behind the scenes, that's what happens when you call a function. Right? It's actually very simple at the end of the day. And you probably can figure out already that it's just an abstraction that is, functions are all just eye candy, okay? Functions are meant to make our lives easier to program. Technically, you don't need functions to do anything, right? Anything you can unravel all functions in your code, right? You can just have one monolithic chunk of code, like 5 million lines long, no functions at all. And it does a job. Yeah, okay. There'll be lots of repetition. There'll be lots of not useless, lots of redundant code in there. And it'll be hard to read and understand and manage. Function calls make it easier. And that is the first step in the direction of object-oriented programming, which we'll start looking at from next class onwards, right? Next week. Object-oriented programming is all about abstraction. Now, the beauty of these things is that you get more power by giving power away. How incredible, isn't it? Because stack is a powerful data structure, but it's built on an array, which is even more powerful. But a stack is good at what it does because it takes something really powerful and hides away a lot of its power, so that you can only see so much. And why is that better for programmers? Why is it better for creativity? Why is giving up something eventually beneficial to us? Because at face value, it doesn't seem to make sense. It's not intuitive that if I give something away, it actually benefits me. It's not intuitive at all. However, here is a case where you give up power and actually end up with more power. Why? And my theory is that maybe you can do some experiments in psychology to figure this out. My theory is that by giving things away, you're essentially saying, this thing here is just busy work, is routine work. I need to do this many times repeatedly. And my mind, which is so much more powerful and capable of doing creative stuff, right? Creative, beautiful UI or whatever, creative stuff, you shouldn't be bothered by going through the routine busy work stuff. So I would rather trust someone to do that for me. And I don't want to know the details of how they do it, because knowing the details takes up a lot of time and energy, which you would otherwise have spent doing your own cool work, which is, at the end of the day, that is what you want to happen, right? So therefore, you delegate like a good manager and say, good manager, right? Bad managers will delegate stuff, but also continually keep, pouring over your shoulders, saying, are you doing the right job? Are you doing this? All right, right? No trust there, okay? But good manager has trust and says, I know you can do a good job, so I'm just going to give it to you. I don't know how you're going to do it, but you can do it and give it to me. This is the interface I want. So a function is able to do that by saying, I am willingly giving up my knowledge of the nitty-gritty details of how this is going to happen. And that takes a lot of time, effort, and trust. And trust is not easy to build, right? Everybody knows that, right? It's not easy to build. You need to be like really, really sure that it's going to happen. And when you're sure it's going to happen, you can say, well, you take over and do it because I need to focus on this. And you can do lots and lots of those things and give away power. Giving away power, because those other things need to get done. You need to have some power to do these things. So you give away the power. It's like this person is not a control freak anymore, right? It's not a control freak who needs to know every single byte, every single instruction. That person doesn't need to know. They trust us to do our job because they can do their job. So a function essentially abstracts away a lot of these things and says, you do it however you want. It's a black box. Okay, I trust you. I'll take what you give me and build it into my final product. And that way you can build bigger products. Right? Because then you have your entire world at your disposal, right? You can have a program. You can say, well, you know what? This program is so big, and this part of it is best implemented by someone in, Ethiopia, right? Ship it there. And this one off to the Middle East somewhere, China, everywhere, right? And then everyone will have time frames, right? So 2 weeks, 3 weeks, and so on. And the manager will basically say, let me build stubs like Omar did, right? So I'm going to use stubs for all of those things that are going to eventually come back to me, and I'll build a bigger picture. And as and when each one of them completes them, I'll replace a stub with that person's code base, okay? And test out the whole thing. That is how a bigger product gets built, by trust. Now, instead, if you didn't trust these people and you had to, manage them personally, right? Imagine how hard it'll be, right? From 9 a.m. to 10 a.m., I need to, work with the team in Ethiopia, looking over their code, right? Step by step. From 10 a.m. to 11 a.m., someone in Beijing, right? I got to do this. And the manager has no time to build a full product. And they have to do. So micromanaging and control freakness doesn't get anywhere in, programming. Any job really, but especially so in programming, because programming makes it easy for you to bundle things and ship them away. So you need to have total trust. And you have to build that trust by saying, working with them closely, and finding out or looking over their code and making sure that they do the right thing in the right places, When you're sure, you don't have to look over everything they do from that point onwards. You say, well, you know what? I know you can do it. You can do it, and you get it back, and you integrate everything, and that's how your entire product gets built. Does it all make sense? I think this is how, eventually when you start, building your own product, starting your own company, right? This is essentially what you're going to do, and so it's just an early taste of what you're already going to be doing later on. But that's what it is. Okay. I don't know how long that took. Well, it took at 9:30. Well, a fair bit of time to talk about function calls and how these happen. But I think that would have been useful, right? I think that because it puts a lot of these errors that you get in the compilation process in context, saying, well, if it's an unresolved external, this is what it is, right? Or if I declared a function and the compiler says, hey, this function is supposed to return something, and it's a void function returning a value. Or we've encountered this error, right? Or you say this function is supposed to return something and it's not returning anything, and all of these errors that you'll now be able to make sense of and say, and when it says unresolved external, I don't find this function at all in your code, and you look at your code and it's there, and then you'll know immediately. Well, it's there, but the names are the same, but the parameter lists are the same. Those are the things that you'll automatically look for and make sure everything works. All right, that's all I had to say about functions. If you have any more questions, I'm happy to answer them. Otherwise, we can still play a game. We can still play Sabrina's game. Hey, did we come up with a name for that game? What does the game do? Race. It's a race. It's a race. Star Racer. I think Hannah called it Star Racer. I think it was Hannah. You called it Moving Star. Was it a Moving Star game? I think she called it either Star Racer or Moving Star. Either of those games or names are good. So if you don't have any questions, we can play a round of that and then come back to more questions. Otherwise, I don't have anything in particular, anything else in particular to talk about. Next week we'll talk about objects. Okay. In fact, I'm thinking we'll take the code. Yeah. In fact, that will be the easiest thing to do. We'll take Sabrina's code from last class, and then try and convert that code into object-oriented, right? Because then I think that's easier in many ways. Rather than saying, oh, object-oriented, we'll start a brand new project, this is how objects are done. Yeah, all right. It's always easier to learn a new skill on something that you already know. So far, we know how to do functions, we know how the program works, we know what the game is, the overall logic of the game. It's much easier to learn about objects, taking that and trying to fit that into the object-oriented universe. So yeah, where is it going with function calls? Why is it one step in the in object-oriented programming direction? Because it abstracts away and builds trust. Objects are just exactly the same as that, except it's not for code anymore, it's for data. Object-oriented programming is just the functional paradigm applied to data, not to code, right? The functional paradigm applied to code gives you functions, right? The functional paradigm applied to data gives you objects. An object is nothing but, you have this really, let's take an array. Array is capable of doing a lot of things. But if you give that really, really powerful thing to someone, and they don't know how to use it, they could, tank the whole system. So therefore, I'm going to take that big object, the array, which is capable of a lot of things. I'm going to hide things away, right? So now this object, this new object, which contains the old object, the new object contains the old object inside of it, but you can't call it the old object anymore because it's lacking some of the power. Yes, so you got to give it a new name. And so this new object is called a stack. It's called the old objects inside of it, except that a lot of the power of the old object is hidden. Nobody can see it anymore, right? That is object-oriented programming, where you say, I'm going to create something which is inside a black box. Nobody can see what's inside. However, it gives a few visibility, windows, right? Saying, well, this is a really complex object. Don't ask me how to do things, but I can do things A, B, and C. You can ask me to do A, B, or C. Those are the only three things I can do. And it'll give you hooks for these things. And these hooks are called API calls, right? APIs, application programming interfaces, right? APIs, you would have probably encountered the term API before. An API is essentially what is visible for you to hook onto and make the thing do something when the thing itself could be really, really big. However, there's only three parts of it that is exposed to us. Those three things are the API. So that's why when you go onto the internet and say, I'm going to do this, graphic game, right? Graphics, and it has a lot of these things. I'm going to use a software developer toolkit or a library, right? A graphics library like OpenGL or something like that. A graphics library that contains lots and lots of really interesting calls. May contain a call in a graphics library called remove hidden lines in this wireframe, right? One function call. Say, here's a wireframe model, remove all the hidden lines, meaning, you only see the surfaces and none of the lines behind it, right? So that one call. However, to do that, you have to do a lot of complex processing on the back end. That function that removes hidden lines, you need to find out which parts of which lines are hidden. Yes, that's not a simple algorithm. So it has to do a lot of these things. However, the person who says, here's an object, remove the hidden lines, doesn't need to know that complex logic. You just say remove that, right? And they'll just go and do that. And and so when you get these libraries from out there, you also get documentation. In the documentation for the library, the developer of the library will publish the API of the library, meaning I've got this enormous library which can do a lot of really sophisticated things, right? Data mining, infer the the mean of this distribution, whatever it is, it has that. However, you only need to know these three things. Even though it's a vast library capable of doing these incredible things, you only need to know these three things. These three things are remove hidden lines, or calculate the mean, or right. Those are the only things available and visible to external users. That is called the API. That's what you'll find in the library documentation. So when you go on to Microsoft libraries or any of the C++ libraries, you see the APIs for objects. These are the methods that are permitted to be called on that object. But the object itself is more complex. It does a lot of things. You don't have to worry, but these are the only calls you need to call. So that's what we'll build. Okay. So next class, what we'll do is we'll take this thing. Yeah, we'll take that one-dimensional screen. Yeah, this game that that Sabrina created last class. We'll take that and and say we'll turn the one-dimensional screen into an object, and so that it has its own methods and ways to manipulate it, right? And then we can take the player and turn the player into an object, a player object. So the player object can have a name, it can do certain things, and so on. And we'll learn to work with objects, and it's exactly the same, right? At the end of the day, you'll see that it's exactly the same logic, just packaged in a different way. It's packaged slightly differently to make it easier for yourself when you come back to it after 5 years, right? After 5 years, maybe you get a YouTube recommendation, right? After 5 years, you're working somewhere and you get a YouTube recommendation. Hey, look at this really cool game that was developed by students at Foothill College, right? And you look at it and it's you, right? Hey, there's, Erica and Omar, Sabrina working through this game, and that's them, right? And you see that video, and you'll see that, oh, you know what, that was me creating these libraries or these games, and that's how I do it, and that's essentially what you'll be doing, right? In your life as a programmer, you'll create lots of things. That's why programming is a very creative activity. But what I mean is that, well, all of these arts, any of these arts, is very creative because it gives you opportunities to bring things in your mind that are not physically visible, right? You can actualize these ideas, and that's why it's really, really cool. And so and that is the reason you need object-oriented programming as a tool in your tool chest, because by using objects, using functions, programming in trained ways, okay, and that is another difference between because like I say, anybody can build a house, right? Or anybody can build a shelter, right? So even if you go to caveman, back in the caveman days, anybody can just get a bunch of boulders together, stack them up, and you can move in there, sheltered from rain and wind and wild animals. Okay, so anybody can do that. But where an engineer is different from a regular builder is that the engineer can build and figure out how I can build this in the most comfortable, efficient way, using the least number of stones and giving the most amount of space. Right, so they'll do some calculation saying, the volume of this room is defined by this equation. Let me differentiate it and set it to 0. Find the maximum volume, and so on. Right, like you do in mathematics. That's where engineering comes. Engineering is useful to take some task and say this is the best way you can do it with the least amount of wastage. And so, where was I going with that? So yeah, by using objects and so on and so forth, you'll be able to, programming, right? So you'll see lots of homegrown programmers, and that is one of the things, because programming appears to be easy beginning in the early stages. Just any art, and I don't know, right? I think this is the learning cycle for most humans, right? Initially, anything you take, whether it's music or whatever it is, seems to be quite easy because we're making major strides. So it seems to be easy, and we are all lulled into thinking we're going to be really good at this. This is my cup of tea. This is the place where I'm going to make a difference in the whole world. Okay, because that's a feeling we get when we make rapid advances. We can make rapid advances during the early stages of learning anything, because during the early stages, the steps are quite small and easy and to do, right? But then we get to a place where challenges begin, and that's where lots of students tend to drop off and say, well, you know what, I thought it was easy. Now it's not easy, but something else I found was easy. Because that's easy. Something else was easy because that was, again, the beginning stages, right? So they go and do a lot of beginning stages because everything is easy in the beginning stages. So they end up with lots and lots of beginning stage skills, but they never ever got past that to. And so, so programming, a lot of people could be misled. And because partly also because programming is a young field, okay? Computer programming, I don't know, been around for 50 years maybe, right? So it's very young. And so a lot of people tend to think, because they've never written a program and run it before, they tend to think that, you know, I've written something and it runs, so I'm a programmer. So a lot of people tend to think that they can program, and they start programming just by telling the computer to do things. However, that's like a cave built by a caveman, because they still get things done, right? It'll still work, but it'll be a monolith of a program. It'll be inefficient, it'll be bad, it'll be hard to follow, it'll be hard for other people to work on, right? So they're not good programs. So that they're programs written by non-engineers. And there are lots of companies, even in the Bay Area, okay? Even in the Bay Area, you can go to lots of companies that they employ programmers that aren't true programmers, right? They are programmers who just learn to program on the, by themselves maybe, or without proper training. And they'll get the job done, but you know, that ends up costing the company a lot of money to make 1 cent. They'll probably have to spend like, I don't know, 0.9 cents, or $1.90, right? They have to spend 90 cents of salary and computer, electricity costs and running computer to make that $1. Whereas if they got a programmer to do that, they could probably have got it done for 1 cent and get 99 cents profit out of it. Right. And so, but lots of people, even out there, they're happy with 1 cent of profit. I say, my company's making a profit. It's making 1 cent profit. Okay. No, I got programmers, I'm making a 1 cent profit. No, that's not. A real programmer can make you 99 cents profit for each dollar, not $1, 1 cent. Okay. So, and that is where real programmers are important. And, even though there are so many programmers in Silicon Valley, very small proportion of them are real programmers. Okay. Lots of them are just putting things together, getting them to work, and making some inefficient profit. And a lot of companies are running on inefficient profit because the profit they make is enough to for whatever they to pay their mortgages, right? So and a lot of companies are running like that. Even in fact, even big companies like finance, right? Finance companies before the day when they started employing real hardcore programmers, even finance companies like Visa and all, I'm pretty sure they were using inefficient logic, because they were programmers, they didn't really know how to do things. They're doing things in an inefficient way, but it's still because the credit card companies were making a ton of profit. Okay, using inefficient programmers didn't make a dent in their bottom line. Okay, so they still used inefficient programmers and still made profit. So they managed to fuel the ecosystem that way. But when you get to a product that is purely computational, right? No finances, or these things are not important here. Then you look at the programmers; they'll be really sharp programmers, right? They'll be sharp programmers because the computer has no slack. It doesn't cut you any slack. If it's it'll run fast, and if it's slow, the program will be slow. So if you go to places like that are creating products that are computational, right? Computational products,
it's 0944.
I didn't ask for the time, right? So it says it's right. Oh, maybe I didn't ask for it. Okay, so the programmers employed by the even in places like Google and Microsoft, you'll still find sloppy programmers, right? Because when a company grows beyond 100 people, my experience is 100. Maybe the number is different from other. Beyond 100 people, it is hard to make sure that everybody is a star programmer, right? So what happens is that even in a software focused company, there will be a core group of rock star programmers. Okay, they're responsible for everything, but there'll still be jobs that need to be done by resource type programmers. So, this log file needs to be processed, extract all the number of times, extract all the lines that are in this log file that says accessing something, right? So it doesn't require heavy duty programming knowledge. So resource programmers take care of these things. So when a company gets big enough, you need resource programmers. So not everybody who works there needs to be a top-notch programmer, but chances are higher that if you go to a software-centric house, as opposed to a house that is focused on ads or I don't know, finance or things like that, there's less chance of finding programmers, hardcore programs. Does it all make sense? Right? How about you guys just talk amongst yourself for about 5 or 10 minutes? That's about the end of class, really, 9:50. If you have any questions, call me. I'll come back and answer them. Otherwise, just feel free to talk. Maybe talk about the midterm. Someone has a question. Yu Yang, where are the class? Hey, Yu Yang, you asked a question. Where are the class recordings uploaded to? Wow, you don't know that? Okay. All right. So they're all on, the link that Omar shared. Okay. That's where it is. They're all there. It's not just the class recordings. Sometimes, even one-on-ones with students. In fact, all of my one-on-ones with students also uploaded there, because sometimes during the one-on-one, some of the students ask some questions that could be widely applicable, right? So many students may benefit from the answer to that question. So one-on-ones are also all public, unless we're talking about confidential issues and the student doesn't want to say, oh, I'm going to be talking about my social security number or my grade or something like that. I don't want it to be public. Then that's not public, but otherwise everything is public. Everybody okay? I wouldn't cover any new material today, but I hope this was useful at the end of the day, right? In any case, and I wish you all the very best of luck for your midterm. Put it in perspective, right? Put it in perspective. Look at the formula for the total score and the grade at the end of the quarter. The midterm is not all that important, but it is still important, because only if you master the material that is required up to the midterm, you'll be able to do a good job in the second half. So take care of that. Nothing else? Otherwise, you guys can talk. Hopefully, hey, Ryan, you'll be able to attend from next week, or you think other demands will arise in your company?
I'll try to. Usually my work starts like 8:30, so the first 30 minutes I can probably make, but I can try my best.
Well, pick a good day when you think you have more than 30 minutes, then you can code on that day.
Okay.
So we'll pick a day for coding, and then we have a sufficient number of classes left for every one of you to code. Okay, Minghua, you also have to find a day and time when you can code. Okay, it'll be fun. Talk to all these people. Everybody here has coded it, on screen. Actually, Omar hasn't coded because you were sick. You were sick. Yeah, but you did share your screen for the data representation part, which is really, really cool, right? So I might actually put your graphic in a future. Well, maybe if I revise module 0, maybe I'll put your graphic in that. That's
Yeah,
really nice.
take it.
Yeah. So you can also have a chance to code. But yeah, everybody will get a chance. And it'll be useful. Talk to all the other people who have coded. Okay, I'm pretty sure. Although Sabrina said it was stressful, but it was useful too, right? It was useful and stressful. I hope.
Yeah.
Okay. Great. Okay. So yeah, talk to them. I think you'll also have a great time. Hey, Namrata, did you ever code on screen?
A little bit, but
You did code, huh? I see. I know you've been fairly interactive, so I might have mistaken you as as a person who also coded. But if not, anybody who wants to code can also let me know. And if we've gone through everybody and everybody's had a chance to code, we'll go back and recycle, okay, and give people more opportunities to code also. This is fun. And if you're doing my 2B, again, we don't have formal lectures for 2B. We have informal classes and informal lectures. You can look, they're also on our channel, right? On our YouTube channel. Mostly it's the students meeting to talk amongst themselves, and I only make occasional appearances when I'm invited. But in 2B too, when you're in 2B, if you're interested in doing a group coding project with me, we can do that too, right? Because, again, it's not a formal class. It'll happen at some time that is convenient to you guys, maybe 6 p.m. to 8 p.m. or something like that on a weekend. Then we don't have to have these constraints saying, oh, we need to fit within this time frame and all. We can keep going and do some really cool stuff. And also in 2B, you'll be armed with more powerful tools at your disposal. You'll know a lot more things so that we can bring more to bear on what we're doing. And so we can do more interesting and cool things too. Okay. Yeah. All right. Okay. Anyway, I shouldn't take up any more of your time. Thank you all so much for just sticking around and attending class. And best of luck for your midterm. I hope to see you all. Charlene, you're here too. Nam, hey Nam, you're logging in, but I can never even talk to you, or I can't see you. Okay, so I can't see you. Nobody's seen you. I don't know if anybody has heard you either. So you need to make sure that you can get participation points. As it stands, I don't see you on Reddit. I don't see you in class. So you're automatically only shooting for 85 out of 100 points for your midterm, for your final grade. Yes. So if you're listening to this or watching this video later on, please consider that. Right. Okay. So you should also make a time to code now. Okay. So if you don't have a computer, if you're not set up, make a time to go to Foothill at 8 o'clock. Okay. Go to Foothill at 8 o'clock. I'm sure there are computers in our library or in the STEM center. There's lots of computers at Foothill, right? Decent computers that students can just sit at and use. So you should be able to code at least from one of those computers. All right. Thank you all. Yeah, thank you for making my day again. Happy to see you all. And I will look forward to seeing you all on Tuesday after the midterm. We'll start working with objects then. Okay. Best of luck and have a great weekend.
Professor?
Yeah.
Can I talk a little bit?
Yeah, sure. You can also make a time later if you want, Simon. Okay. So if this time doesn't work,
just like 2 or 3 minutes. Yeah.
Yeah, sure. Okay, cool.
Okay.
Do you want to be
can I talk now?
Is it okay if other people are there, or you can talk, or if you want to talk?
I mean, it's like a little bit personal stuff, so maybe
sorry?
room.
Oh, it's personal?
Yeah.
I have to stop the recording before you start then.
No,
hang on.
okay.
So good thing you told me. Okay. Well,
Okay.
all right. After Rujay and Charlene log out, I'll stop the recording and then you can talk.
Okay.
So can I ask for some question?
Yeah, sure.
It's not that actually related to the current course. Because I ask my question because I'm looking for next quarter's course, and I'm not a student in Foothill. I'm a student in UCSB, and so the UCSB's course is pretty different than Foothill. The difference is because the CS2B and CS2C in my home campus here is the opposite. The sequence is opposite. So I'm looking for.
No. I don't think so. I don't think that is the case. Okay.
Yeah.
Are you talking about UCSD?
Santa Barbara.
Oh, Santa Barbara.
Yeah.
Santa Barbara. I don't know if they can be different from UCSD.
I just
my son went to UCSD. This was the sequence. However, he told me that their equivalent of CS2B and 2C is one course. It's just one course that has both of them in it.
Oh yeah.
Yes.
So the sequence is not really that important, right?
But you have to do it. Even if it's one course, they'll teach you the 2B material first and then do the 2C material. Yeah. So it's one course, but we're just doing it in 2 parts. So you got to do 2B and 2C. Do 2B and 2C, okay? Even though you're at UCSD, do 2B and 2C here with me. I think it'll be useful for you at UCSD.
I'm sorry. The answer question, since I have to choose CS24, that's CS2C here, because the school has some restrictions that all these
Yes.
computer science students has to finish that course here. But I just want to know that CS24 is the equivalent for CS2C. So next quarter, I just want to say that if it's possible for me to study 2B and 2C just at the same time, I just want to know.
All right. That's not a question for me.
It's not hard, right?
For me, it's okay. Okay. I don't care. I don't care if you are able to enroll in 2B and 2C at the same time. Even if you enroll in 2B and 2C at the same time, you cannot work on both of them at the same time. You enroll in both in one quarter, but in the first 6 weeks of the quarter, you've got to be working on 2B stuff, and the second 6 weeks you'll work on 2C stuff, because it's sequential. You can't do, right? It's like a storybook. You can't read the first chapter and the 15th chapter alternate like this. Yes. So we'll cover it sequentially. Even at UCSD, they'll cover it sequentially.
Okay.
So so if you do my 2B, if you want to, what you can do, you have to complete both in one quarter. Are you under a constraint that you have to complete both of them in one quarter?
No, I'm asking because I'll enroll the equivalent of CS2C here in UCSB and taking CS2B info here in the same quarter.
In the same quarter.
Yeah.
Okay. All right. In that case, you could do your 2C at UCSD and do 2B here. But you can't do it the other way around, I think. You can't do your 2B there, because 2C here, then Foothill will say, where's your 2B?
I know. So I
The
just want
person
to know
talk
that
to-
is that
No. Talk to the dean. Talk to the dean of STEM.
Yeah.
And say that you're at UCSD and you can get these prereq clearances because of equivalence courses. There's something called what is that site? It starts with an A. It tells you what the equivalent courses are, and then you can tell him or her, right? This is what I need to do. Can you clear me? And they'll give you special permission. I don't have the authority to give you that permission.
Okay. Okay, I have another very strange question. Just for
sure.
In 1 hour ago that you said that it's not good to do leak code. I don't because I was studying some algorithm competition back in high school, and I'm now studying ACM. So in fact, I'm not really training on leak code. I'm training on some websites like Codeforces. So I wonder why it's not really good. Because
Why it's not
I don't
related?
know, Rich.
I missed your question. I missed the last part of your question. You wonder why it's not?
Why it's not good, since you said that it's not good.
No, I didn't say it's not good. I know. I didn't say it's not good. You should train, but you should make sure that you also master the principles and the concepts before you execute those. And the reason I said these other sites are not good for exams is because they'll just focus on the finished product, when you need to know many more things before you get there. And that is the reason I say, do it at a university or a college where they'll teach you everything, and then you'll be good at that one thing that is required. I don't know. I that's my understanding of your question. Okay, I don't know what your question was completely, but
yeah.
Did that answer your question?
Yeah. Since I'm often doing a lot of coding.
You asked me about other sites where and you should continue to train with all these other sites. That's fine, but you also pick up the fundamentals and the concepts.
Okay.
Yeah.
Thanks.
Awesome. No worries. Charlene, are you here? Charlene? Oh, maybe she should have logged out. Let me.
Okay.
Oh, wait. I need to.
Is it stop recording?
I don't want to. It says I don't want to record. Yeah. Okay. Just you and me. You can ask now.
Okay.
Oh, I need to stop the recording. Hang on.
Yeah. Just.